Welcome! In this video, we'll explore LeetCode problem number 930, titled Binary Subarrays with Sum. This problem challenges us to count the number of contiguous subarrays in a binary array whose sum equals a given goal. We'll break down the problem, analyze the solution, and discuss its complexity. Let's dive in. In this problem, we are working with a binary array called nums, which contains only zeros and ones. Additionally, we are given an integer goal. The goal is to determine how many contiguous subarrays within nums have a sum equal to this goal. A subarray is any continuous portion of the array, and the sum of a subarray is simply the sum of all its elements. For the input, we are provided the binary array nums and the integer goal. The output will be a single integer representing the number of subarrays in nums whose sum is exactly equal to goal. Let's look at an example to better understand the task. Consider the array nums equals 1, 0, 1, 0, 1, and the goal 2. Here, we need to find all contiguous subarrays that add up to 2. The output for the given example is 4, and here's why. The subarrays in nums that sum up to goal equals 2 are as follows. The first subarray is 1, 0, 1, which starts at index 0 and ends at index 2. The second subarray is 0, 1, 0, starting at index 1 and ending at index 3. The third subarray is 1, 0, 1, starting at index 2 and ending at index 4. Finally, the fourth subarray is 1, 0, starting at index 3 and ending at index 4. In total, there are 4 subarrays that meet the criteria. Now, let's consider another example, where nums equals 0, 0, 0, 0, 0, and the goal is 0. In this case, we need to count all subarrays that sum to 0. The output for this example is 15. This is because every possible subarray in nums sums to 0, as all elements are 0. To calculate this, we can group the subarrays by their lengths. First, there are 5 subarrays of length 1, 0, 0, 0, 0, 0. Then, there are 4 subarrays of length 2, 0, 0, 0, 0, 0, 0, 0, 0. For subarrays of length 3, we have 0, 0, 0, 0, 0, 0, 0, 0, 0, giving us 3 subarrays. Subarrays of length 4 are 0, 0, 0, 0, 0, 0, 0, 0, which adds 2 more subarrays. Finally, there is one subarray of length 5, 0, 0, 0, 0, 0. When we add them all together, we get 5 plus 4 plus 3 plus 2 plus 1, which is 15. Let's look at one more example to solidify our understanding. If nums equals 1, 1, 1, 1, 1, and the goal is 3, we need to find all subarrays that add up to 3. In this case, the output is 3, because there are exactly 3 subarrays that sum to goal equals 3. These subarrays are 1, 1, 1, starting from index 0 to 2, 1, 1, 1, starting from index 1 to 3, and 1, 1, 1, starting from index 2 to 4. Now, let's consider the constraints of the problem. The length of the array nums can go up to 30,000 elements, so we need to make sure our solution is efficient. Each element in nums is either 0 or 1, and the goal is a non-negative integer that does not exceed the length of nums. It's also important to handle edge cases. For example, if goal equals 0, we need to count subarrays consisting entirely of zeros. If goal is greater than the total number of ones in nums, the output will be 0, as no subarray can meet that condition. By considering these constraints and edge cases, we can ensure our solution is both correct and optimized. To solve the problem of counting binary subarrays with a sum equal to the given goal, we can take several different approaches, each with its own trade-offs. The most basic method is the brute force approach, where we generate all possible subarrays from the input array and compute their sums individually. If the sum of a subarray matches the goal, we increment our count. While this method is simple and easy to understand, it involves nested loops to enumerate every subarray and an additional loop to compute the sum of each subarray. As a result, it has a time complexity of n cubed, which makes it impractical for large input arrays. On the bright side, it does not require any extra space, so the space complexity is 1. However, the inefficiency of this approach lies in its repeated recalculations, making it clear that we need to find a more optimized strategy for larger datasets. Now, we can improve upon the brute force approach by introducing prefix sums. The idea here is to avoid recalculating the sum of every subarray from scratch. Instead, we pre-compute a prefix sum array, where each element represents the cumulative sum of the array up to that index. Using this array, we can calculate the sum of any subarray in constant time by subtracting the prefix sum at the start of the subarray from the prefix sum at the end of the subarray. This optimization reduces the time complexity to O(n squared), as we still need to check all possible subarray start and end points, but the calculation of each subarray sum is now O(1). The space complexity increases slightly to O(n), due to the storage of the prefix sum array. While this method is a significant improvement over the naive brute force approach, it is still not efficient enough for very large arrays, as the time complexity remains quadratic. The most efficient approach leverages a hash map in combination with prefix sums. Here, the key insight is that for a subarray to have a sum equal to the goal, the difference between the current prefix sum and the goal must have been seen previously in the array. By storing the count of each prefix sum in a hash map as we traverse the array, we can directly check if the required difference exists in constant time. For each prefix sum, we look up prefix_sum goal in the hash map, and the value associated with this key gives us the number of valid subarrays ending at the current index. This approach allows us to count subarrays in linear time, achieving a time complexity of O(n). The space complexity remains O(n) due to the hash map, but the trade-off is well worth it given the significant improvement in runtime efficiency. This method is particularly well suited for large arrays, making it the optimal solution for this problem. To summarize, the hash map with prefix sums approach is built on several key observations. First, the cumulative nature of prefix sums allows us to efficiently identify subarrays with a given sum. Second, by calculating the difference prefix_sum goal, we can determine whether a subarray with the desired sum exists using previously seen prefix sums. The hash map enables quick lookups and eliminates the need for nested loops, making the process highly efficient. While alternative methods like brute force and prefix sum enumeration are more intuitive, they are computationally expensive for large inputs, with time complexities of O(n cubed and O(n squared, respectively. The hash map solution achieves O(n) time complexity, balancing efficiency with a slight increase in space usage. This trade-off makes it the best choice for solving the problem on large datasets, providing both scalability and speed. In this problem, we are tasked with finding the number of contiguous subarrays in a binary array whose sum equals a given value, referred to as the goal. Since the array contains only zeros and ones, we need an efficient algorithm to handle large inputs, up to lengths of 10,000. The optimal approach utilizes the concept of prefix sums combined with a hash map. Here, the prefix sum helps us track the cumulative sum of elements as we iterate through the array, while the hash map stores the frequency of each prefix sum encountered. This allows us to efficiently check if any subarray sums match the goal. We initialize the prefix sum to 0 and pre-populate the hash map with a key value pair of 0, 1, which accounts for cases where a subarray starting at the beginning of the array has a sum equal to the goal. Now, let's define the key variables: the prefix sum variable to maintain the running sum, the hash map to store prefix frequencies, and a result variable to count the valid subarrays. With these in place, we're ready to dive into the algorithm. To solve the problem, we iterate through the binary array and process each element one by one. For each element, we add its value to the prefix sum, updating our running total. Next, we calculate the complement, which is the difference between the current prefix sum and the goal. This complement represents the prefix sum that, if removed from the current total, would result in the desired goal. We then check if this complement exists in our hash map. If it does, it means there are subarrays ending at the current index whose sum equals the goal. The frequency of the complement in the hash map tells us how many such subarrays exist, and we add this count to our result. Finally, we update the hash map to include the current prefix sum, incrementing its frequency. This ensures the hash map reflects the prefix sums encountered so far. After completing the loop, the result variable holds the total count of subarrays that meet the criteria. The key to this approach lies in understanding the properties of prefix sums and leveraging a hash map for optimization. The prefix sum at any index represents the total of all elements from the start of the array up to that index. If we take two prefix sums, their difference gives the sum of the subarray between them. Therefore, if the difference between two prefix sums equals the goal, we know the subarray in between satisfies the condition. Rearranging this equation, we see that the presence of a prefix sum equal to the current prefix sum minus the goal is what we need to identify valid subarrays. This is where the hash map comes in. It lets us store and retrieve prefix sums efficiently. By maintaining the frequency of each prefix sum, we avoid recalculating subarray sums repeatedly, achieving an O(n) time complexity. Additionally, this algorithm handles edge cases, such as arrays with all zeros or ones, and even when the goal is 0, thanks to the initial hashmap setup. To implement this algorithm effectively, two main data structures are used. First, the hashmap, or prefix_count, is the core of our solution. It stores the frequency of each prefix sum encountered so far, allowing for constant time lookups. This enables us to check the existence of complements and retrieve their frequencies efficiently. Second, we rely on variables like prefix_sum and result to maintain the running total and the count of valid subarrays, respectively. The prefix_sum variable tracks the cumulative sum as we iterate through the array, while the result variable is increment whenever we find subarrays that meet the goal. Together, these structures ensure the algorithm operates efficiently in both time and space. Analyzing the complexity of this algorithm, we see it performs exceptionally well. The time complexity is O(n), because we iterate through the array once, performing constant time operations at each step, such as updating the hashmap and calculating the complement. The space complexity is also O(n), as the hashmap may store up to n unique prefix sums in the worst case. To illustrate how this works, let's consider an example. Suppose the input array is 1, 0, 1, 0, 1, and the goal is 2. We initialize our variables. Prefix_sum starts at 0, prefix_count is preloaded with 0, 1, and result is set to 0. Now, we'll process each element in the array step by step. Starting with the first element, nums 0 equals 1, so we add it to prefix_sum, making it 1. The complement is calculated as 1 minus 2, which is minus 1. Since minus 1 does not exist in the hashmap, no subarrays are found. We then update the hashmap to include the current prefix sum, resulting in 0, 1, 1, 1. At index 1, nums 1 equals 0, so prefix_sum remains 1. The complement is still minus 1, which is not in the hashmap, so no subarrays are found. We update the hashmap again, making it 0, 1, 1, 2. At index 2, nums 2 equals 1, updating prefix_sum to 2. The complement is now 2 minus 2, which is 0. Since 0 exists in the hashmap with a frequency of 1, we add 1 to result. The hashmap is then updated to 0, 1, 1, 2, 2, 1. Next, at index 3, nums 3 equals 0, so prefix_sum remains 2. The complement is still 0, and the hashmap shows a frequency of 1 for this value. We add 1 to result, bringing it to 2. The hashmap is updated to 0, 1, 1, 2, 2, 2. Finally, at index 4, nums 4 equals 1, updating prefix_sum to 3. The complement is 3 minus 2, which is 1. The hashmap shows a frequency of 2 for this value, so we add 2 to result, making it 4. The hashmap is updated to 0, 1, 1, 2, 2, 2, 3, 1. By the end of the iteration, result holds the value 4, which is the total number of subarrays with a sum equal to the goal. This example demonstrates how the algorithm efficiently counts subarrays by combining prefix sums and hashmap lookups, avoiding redundant calculations and ensuring optimal performance. This implementation effectively solves LeetCode problem number 930, binary subarrays with sum, using a prefix sum and hashmap technique. Here's the detailed explanation. The function number subarrays with sum takes two inputs, the binary list nums and the target sum goal. The goal is to count the number of contiguous subarrays that sum up to the value goal. #### step-by-step explanation. Initialization ***. Count is initialized to 0. This variable will store the total number of valid subarrays found. Prefix_sums is a dictionary initialized with 0, 1. This hashmap stores the frequency of each prefix sum encountered. The entry 0, 1 accounts for cases where a subarray starting from the beginning of the list equals the target sum. Current_sum is initialized to 0. This variable keeps track of the cumulative sum of elements as we iterate through the list. Iterate through the list asterisk. As we loop through each element in nums, we add the current element, number, to current_sum, updating the running total. The key observation is that if current_sum goal exists in prefix_sums, it means there is at least one subarray ending at the current index whose sum equals goal. We add the frequency of current_sum goal to count. After processing the current element, we update the prefix_sums dictionary. If current_sum already exists, we increment its count, otherwise, we add it to the dictionary with a count of 1. Return the result asterisk. After processing all elements, count contains the total number of subarrays whose sum equals goal. This result is returned. ### key insights. 1. Efficiency asterisk. The algorithm runs in O(n) time because we traverse the array once and perform constant time operations for each element, #map lookups and updates. 2. Space usage asterisk. The space complexity is O(n) in the worst case, where all prefix sums are distinct. 3. Edge case handling asterisk. If nums is empty, the function returns 0 since no subarrays exist. It correctly handles cases where goal is 0, as the #map initialization accounts for prefix sums starting from 0. This approach ensures optimal performance and correctness for all valid inputs, adhering to the problem's constraints. This is the Java implementation of the LeetCode problem number 930, binary subarrays with sum. The logic mirrors the Python solution, utilizing a #map to store prefix sums and their frequencies. Key differences include the use of explicit type declarations in Java, the #map class for prefix sums, and Java's syntax for loops and conditional statements. The solution iterates through the array while maintaining a running sum and checks for complementary prefix sums to compute the count of subarrays that match the target sum. Here, we begin with the first example where the input array is 1, 0, 1, 0, 1, and the goal is 2. We start by initializing our variables. Count is set to 0, which will hold the number of subarrays that sum to the goal. The prefix_sums dictionary starts with 0, 1, which helps us track how many times each prefix sum has occurred. Finally, current_sum is initialized to 0, which will represent the cumulative sum as we iterate through the array. Now, for the first element, 1, we add it to current_sum, making it 1. The difference between current_sum and the goal, which is -1, is not in prefix_sums, so no subarrays are found yet. We update prefix_sums to reflect the new prefix sum of 1. For the second element, 0, adding it to current_sum keeps the sum at 1. Again, the difference of -1 is not in prefix_sums, so no subarrays are counted. We update prefix_sums to show that the prefix sum of 1 has now occurred twice. Then, for the third element, 1, we add it to current_sum, which brings it to 2. This time, the difference between current_sum and the goal, which is 0, is in prefix_sums. Since the difference of 0 is in prefix_sums, we add the count of prefix_sums, 0, which is 1, to count, making count equal to 1. We then update prefix_sums to include the new prefix sum of 2. For the fourth element, 0, adding it to current_sum keeps the sum at 2. The difference of 0 is still in prefix_sums, so we add prefix_sums, 0, which is 1, to count, making it 2. Again, we update prefix_sums to reflect that the prefix sum of 2 has now occurred twice. Finally, for the fifth element, 1, adding it to current_sum brings it to 3. The difference between current_sum and the goal, which is 1, is in prefix_sums. We add prefix_sums, 1, which is 2, to count, making the final value of count equal to 4. After updating prefix_sums to include the prefix sum of 3, we conclude that there are 4 subarrays in this example that sum to the goal. Now, we move to the second example where the input array is 0, 0, 0, 0, 0, and the goal is 0. As before, we initialize count to 0, prefix_sums to 0, 1, and current_sum to 0. For the first element, 0, adding it to current_sum keeps the sum at 0. The difference between current_sum and the goal, which is also 0, is in prefix_sums. We add prefix_sums, 0, which is 1, to count, making it 1. We then update prefix underscore sums to reflect that the prefix sum of 0 has now occurred twice. For the second element, 0, adding it to current underscore sum again keeps the sum at 0. The difference of 0 is still in prefix underscore sums, so we add prefix underscore sums, 0, which is now 2, to count, resulting in a count of 3. We update prefix underscore sums once more to show that the prefix sum of 0 has occurred 3 times. Next, for the third element, 0, the same calculation applies. Adding the third 0 to current underscore sum keeps it at 0. The difference of 0 is again in prefix underscore sums, so we add prefix underscore sums, 0, which is now 3, to count, making it 6. We update prefix underscore sums to indicate that the prefix sum of 0 has now occurred 4 times. For the fourth element, 0, the process repeats. Adding it to current underscore sum keeps the sum at 0, and since the difference is still in prefix underscore sums, we add prefix underscore sums, 0, which is 4, to count, bringing it to 10. We update prefix underscore sums to reflect the prefix sum of 0 occurring 5 times. Finally, for the fifth element, 0, adding it to current underscore sum once again keeps the cumulative sum at 0. The difference of 0 is in prefix underscore sums, so we add prefix underscore sums, 0, which is now 5, to count. This gives us a final count of 15. After updating prefix underscore sums to record the prefix sum of 0 occurring 6 times, we conclude this example with 15 subarrays that sum to the goal. In the third example, the input array is 1, 1, 1, 1, and the goal is 3. We initialize count to 0, prefix underscore sums to 0, 1, and current underscore sum to 0. For the first element, 1, adding it to current underscore sum brings the sum to 1. The difference between current underscore sum and the goal, which is -2, is not in prefix underscore sums, so no subarrays are found yet. We update prefix underscore sums to include the prefix sum of 1. For the second element, 1, adding it to current underscore sum gives a sum of 2. The difference of -1 is still not in prefix underscore sums, so no subarrays are counted. We update prefix underscore sums to include the prefix sum of 2. Then, for the third element, 1, adding it to current underscore sum brings it to 3. This time, the difference between current underscore sum and the goal, which is 0, is in prefix underscore sums. Since the difference of 0 is in prefix underscore sums, we add prefix underscore sums, 0, which is 1, to count, making it 1. We then update prefix underscore sums to include the new prefix sum of 3. For the fourth element, 1, adding it to current underscore sum brings the sum to 4. The difference between current underscore sum and the goal, which is 1, is in prefix underscore sums. We add prefix underscore sums, 1, which is 1, to count, making the final value of count equal to 2. After updating prefix underscore sums to include the prefix sum of 4, we conclude that there are 2 subarrays in this example that sum to the goal. This demonstrates how the algorithm efficiently counts subarrays using the prefix sums approach. Here, we analyze the time complexity of the solution. The algorithm processes the array nums in a single pass using a sliding prefix sum technique. This means that the loop iterates through each element of the array exactly once, where n is the size of the array. For every iteration, we perform a constant time addition to update the current underscore sum and look up the dictionary prefix underscore sums to check for current underscore sum goal. Additionally, we update the dictionary to keep track of the frequency of prefix sums, which are all O1 operations on average. When we combine these operations, the total cost per element remains constant, and since the loop processes all n elements, the overall time complexity is O(n). This makes the solution highly efficient in terms of time usage. Now, we focus on the space complexity of the algorithm, which is determined by the memory used to store the prefix underscore sums dictionary and a few auxiliary variables. The dictionary prefix underscore sums keeps track of the frequencies of prefix sums encountered as we iterate through the array. In the worst-case scenario, where all elements are 1s, the prefix sums will be distinct for each element, resulting in n unique entries in the dictionary. This means the space required for the dictionary scales linearly with the size of the input, O(n). Apart from the dictionary, the algorithm uses a few additional variables such as count, current underscore sum, and loop counters, all of which require constant space, or O(1). Therefore, the overall space complexity is dominated by the dictionary, giving us O(n) space usage in the worst case. Let's break down the best, average, and worst case scenarios for the algorithm. In the best case, even if the number of unique prefix sums is minimal, the algorithm still has to iterate through the entire array once, so the time complexity remains O(n). In the average case, the distribution of zeros and ones in the array determines the number of unique prefix sums, but the algorithm's efficiency is unaffected since it still processes the array with O(1) operations per element, keeping the time complexity at O(n). Lastly, in the worst case, where the array contains only one s and thus all prefix sums are unique, the algorithm still maintains O(n) time complexity. However, the space complexity reaches O(n) as the dictionary grows to store all n unique prefix sums. Overall, the algorithm consistently maintains linear time complexity regardless of the input distribution. Let's compare the optimized approach to a brute force solution. In a naive approach, we would generate all possible subarrays and check if their sum equals the desired goal. Generating all subarrays for an array of size n requires O(n) squared operations, and calculating the sum of each subarray in the worst case takes O(n), resulting in a total time complexity of O(n) cubed. On the other hand, the brute force approach has a space complexity of O(1), since it doesn't require any additional data structures. In contrast, the optimized solution makes use of a prefix sum and a hash table to count frequencies, which avoids explicitly generating subarrays. This reduces the time complexity to O(n), significantly improving efficiency. While the space complexity increases to O(n) due to the dictionary, this trade-off is justified by the drastic reduction in time complexity, making the optimized approach far superior overall. Finally, we validate the big O analysis of the optimized solution. For time complexity, the algorithm loops through the array nums exactly once, performing constant time operations such as hash table lookups and updates for each iteration. Since there are n iterations, and each operation within the loop is O(1), the total time complexity is O(n). For space complexity, the dominant factor is the prefix underscore sums dictionary, which stores up to n unique prefix sums in the worst case. This results in O(n) space usage. Combining these, the optimized solution achieves O(n) for both time and space complexities, which is a substantial improvement over the O(n) cubed time complexity of the brute force approach. This efficiency highlights the power of leveraging prefix sums and hash tables for problems like these. One of the most common mistakes in this problem arises from not handling edge cases properly. For example, if the input array, nums, is empty or the goal is 0, failing to account for these scenarios can lead to runtime errors or incorrect results. To avoid this, it's crucial to test your solution explicitly with these types of inputs during development. Another frequent error happens with the prefix sum approach, where some overlook the need to account for the goal in the difference calculation. Specifically, the correct logic involves checking prefix underscore sum goal, and missing this step results in inaccurate subarray counts. Similarly, while the sliding window technique is powerful for many problems, it doesn't directly work here without additional adjustments. Because the array consists only of zeros and ones, the sum can quickly overshoot the goal, requiring careful window adjustments. Lastly, brute force methods, which involve checking all possible subarrays, are inefficient for larger inputs due to their O(n) superscript 2 complexity. Instead, aiming for an O(n) solution using a hash map is a much better approach for both performance and scalability. Another pitfall to watch out for is confusion when updating the hash map during a prefix sum implementation. If you forget to update the hash map after calculating the current subarray count, this can lead to off-by-one errors or missed subarrays entirely. It's important to update the map immediately after processing each prefix sum to ensure accuracy. From an interview perspective, one key insight is that this problem is a variation of the subarray sum equals k problem, which is LeetCode number 560. The binary nature of the input array simplifies calculations, making the prefix sum approach particularly effective. Interviewers often focus on your ability to optimize the solution to O(n) using a hash map. Be prepared to explain why this approach is efficient compared to brute force methods and how it avoids unnecessary computations. Recognizing patterns is another critical skill. Many subarray problems can be tackled with either prefix sums or sliding windows. Identifying the right pattern early can save valuable time. Additionally, discussing edge cases, such as when the goal exceeds the total sum of the array or when all elements are zeros, demonstrates a thorough understanding of the problem and solution. This problem also has strong ties to several related problems that use similar techniques. For instance, LeetCode number 560, subarray sum equals k, involves counting subarrays with a specific sum using prefix sums in hash maps. LeetCode number 1248, count number of nice subarrays, shifts focus to counting subarrays with a specific number of odd numbers, but it still heavily relies on prefix sums. Another related problem is LeetCode number 974, subarray sums divisible by k, where modular arithmetic is added into the mix to count subarrays divisible by a given number. Finally, LeetCode number 525, contiguous array, tackles a binary array problem where you look for the longest subarray with an equal number of zeros and ones. These problems share a common thread in leveraging prefix sums to reduce the complexity of counting or tracking specific subarray properties. By practicing these problems, you'll develop a deeper understanding of how to apply prefix sums and hash maps effectively in different scenarios. Now let's consider some alternative approaches and their trade-offs. The brute force method is the most straightforward to implement. In this approach, you iterate through all possible subarrays and calculate their sums, but its in superscript 2, time complexity makes it impractical for larger inputs. This method is only suitable when the constraints are small. The sliding window approach, on the other hand, offers complexity and is often a go-to technique for many subarray problems. However, in this specific problem, the binary nature of the array makes the sum harder to control, requiring additional logic to adjust the window correctly. This can make the implementation trickier and less intuitive. The optimal solution for this problem combines prefix sums with a hash map, offering both time complexity and a straightforward implementation. Here, the hash map stores prefix sums and their frequencies, allowing you to quickly check for the difference prefix_sum goal. While this approach is efficient, the trade-off is that it uses extra space for the hash map. Understanding these methods and their strengths and weaknesses ensures you can adapt to different variations of subarray problems effectively. Great job! To summarize, we learned how to solve binary subarrays with sum efficiently using prefix sums and hash maps. This approach is both time and space efficient. Remember, mastering these techniques will help you solve similar problems in interviews and real-world scenarios. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!